In this video we're going to be covering this integral, which is for a function I of n, which equals the integral from 0 to infinity of e to the negative x to the power of n, where n is a real value, so this is dealing with a completely real valued integral, but n is strictly set so that it is a positive real number, i.e. n is greater than or equal to 0. In fact, actually, we would have to have that n is greater than 0, so please change this inequality to n being greater than 0 as opposed to being n greater than or equal to 0. Okay, now the way in which I'm going to represent this function is in terms of the gamma function. So the gamma function looks very similar to this, but instead of having x to the power of n, it just has an x here. So let's have a look at that. So gamma of n is equal to the integral from 0 to infinity of x to the power of n minus 1 e to the negative x. Now, the fact that we don't have x to the power of something out here is not necessarily a big deal. I mean, essentially we do. This is x to the power of 0 out the front. So we've got that. The big difference is obviously that we have x to the power of n here, whereas in the gamma function we just have x to the power of 1. So when I'm looking to convert it from this form into this form here, I want to make a transformation that will allow for this e component to be definitely present. And so therefore, when I'm looking at the substitution to make from here, it's a fairly simple one. I want this, instead of it being x to the power of n, I want it to be something else, another variable, which for the purposes of this tutorial, I'm just going to let equal u. Then, by doing so, I'm going to have something at the front after I rearrange, the dx du component, but I will have e to the negative u. And from there, that should be in the form of the gamma function, which it actually turns out to be. So that's what we're going to do. We have u is equal to x to the power of n, which means du dx, just using basic differentiation, is equal to nx to the n minus 1, which is equal to n u to the power of 1 over n. So if you're wondering where that came from, remember u is equal to x to the power of n. If I want to isolate x is obviously then u to the power of 1 over n. So substituting that in and then expanding with the indice laws, if I remember, that just equals n u to the power of n minus 1 excuse me, over n. Now we want this represented in the form of dx is equal to something du. We need that obviously in order to make the proper substitution for the integral. So rearranging it, this is very simple to do. Just bring this dx here up to this side and then divide this component through onto this side. We have dx is equal to du, over n u to the n minus 1 over n, which is just equal to 1 over n u to the power of 1 over n minus 1 du. So now what we've been able to do is we've been able to make this transformation of u is equal to x to the n and see how it changes the dx component into a du component. And so the next component that we have to do, because we're dealing with a definite integral here, is that we need to also change the limits. So at x is equal to 0, we're now replacing it with u, which equals x to the power of n. So u, which equals x to the power of n here for the lower bound, is equal to 0 to the power of n, which is just equal to 0. And that holds for n is greater than 0. And then we find that as x goes to infinity, u itself goes to infinity. Infinity to the power of n is obviously just equal to infinity when n is positive. And so we see that the bounds that we have here remain unchanged. So this stays exactly the same, but what we're going to have here is e to the negative u, and then for the dx component, this is going to be replaced with this component that we have here. And that's what we see in the next line. So we have I of n, which is equal to the integral from 0 to infinity of e to the negative x to the n dx is equal to the integral from 0 to infinity e to the negative u. This dx gets replaced with this component here, which we derived just a second ago, which is 1 over n u to the 1 over n minus 1 du. 1 over n is just a constant, so I'm going to draw that out the front, which is what I have here. The limits, as I forgot to mention, and the limits remain unchanged, which we just went through. So we've got the integral from 0 to infinity, u to the power of 1 over n minus 1 e to the negative u du. And we see that with our definition of the gamma function, that's exactly what we have. So in this case here, our n value is just equal to 1 over n. So that's just equal to 1 over n gamma of 1 over n. And so now we've been able to take this integral, which is the function, which is the integral of I of n, which equals the integral from 0 to infinity of e to the negative x. Let me restate that. I of n, which equals the integral from 0 to infinity of e to the negative x to the power of n dx, is equal to 1 over n gamma of 1 over n. And this holds for all real values of n that are greater than 0. Okay, well, that's all we have for this video. If you like the video, please hit like. If there's any comments or observations or any further areas you would like explored within this video, please leave a comment and I'll do my best to get back to you. As with all of my other videos, I take requests as part of this channel that I'm running. So if you have an integral that you would like to have covered, please either comment here or send me a direct message over YouTube. And if I'm able to solve the integral and I have time to be able to do it, I will certainly put it together and I will upload it. Otherwise, have a great day.